Kia ora, Year 12. Today's lesson is going to be on the Poisson distribution, but I need to be somewhere else. So what I thought I'd do is make a quick video covering the main part of the material, and you can work through that. So if you're watching this and it's still the holidays, that's great. It means that in class on Monday next week, period 2, you can get straight into doing some practice. But if it is Monday of week 2, welcome back, and let's get going. So what I want to do first is to recap what we've done with the Poisson distribution. I'm not going to do any examples in this video to keep it reasonably short. I might do a separate video with examples. And if you're watching this early and you've got stuck on some, feel free to email me and I'll focus on those. Okay, so the Poisson distribution, as we know, is a discrete distribution. That means that it takes on counting values, right? So 0, 1, 2, and so on. And it's called the distribution of rare events. There are a few conditions that we've got to have, and one of them is that events have to occur randomly, and it measures something discrete per continuous interval. So examples here are the elusive number of lumps of hokey pokey per ice cream scoop, the number of tornadoes in Wellington per year. What else could we think of? What happened there? Number of goals in a World Cup match. Now, we can argue about how well the assumptions fit each of those situations, but basically we have to have something we can count per unit of time or space, and we also have to assume that the rate is uniform over the interval and that occurrences of the thing are independent of each other. So definitely with the World Cup match goals one, you might argue that that's not that realistic. But the Poisson distribution is a pretty useful one in real life. So the most important thing practically is how we find one of them. And this is the formula. And it's got one parameter, and that parameter is called lambda. Just a thing to note, if you're playing around with your graphics calculator, when you go to do the Poisson distribution on that, we'll look at that when I'm back, you're going to use PPD and PCD under the dist menu. So this is no use for your A-level exam, but it will be for level 3 next year. That lambda is actually called mu, and you'll see that quite often that they're used interchangeably. Lambda it's pretty cool because it's both the mean and the variance of a Poisson. All right, so that makes it very, very simple to work with. So one thing we found out last term that was really nice for finding a whole lot of probabilities from a Poisson is that once we found one of the Poisson probabilities, so once we've found P of x equals 0, we can build up very quickly to the other ones by using this recurrence relation. For example, the probability that x equals 1 will just equal lambda over 1 times the probability before it. And then the probability that x equals 2 will equal lambda over 2 times the probability that x equals 1. So you'll get to practice that in the exercises. One thing to note there is not to round too hard, so try and hold a whole lot of decimal places in your calculator. Okay. The next thing that we're going to look at, and this is new today, is a really, really cool feature of Poisson distributions, and that's that I can add them together. So suppose that I've got one Poisson distribution with lambda of 4, and we'll call that random variable x. So x is distributed Poisson with lambda of 4, and y is distributed as a Poisson distribution with lambda of 6. Then if we want to find out something about the total, that will be distributed as Poisson, and all we have to do is to add those two values together. So the classic example would be the number of buses going one way along a street in a half-hour period and the number of buses going the other way in a half-hour period. If we wanted to work out the total number of buses going past in either direction, we just add up the two averages and go from there. And again, we'll do some examples later on, but that's the basic result for now. Okay, slightly easier to think about than that is that often we have to change lambda around, and this is what we call adjusting for different time intervals. And this is really straightforward as well. We just use proportional reasoning. So if we've got 6 hurricanes per year on average, lambda is equal to 6. If we're asked to figure out something about how many hurricanes in a month, obviously that lambda of 6 doesn't apply because it's per year. So we've got 6 for 12 months. What lambda are we going to use for 1 month? Well, we're just going to divide that number by 12. So we'll use lambda equals 0.5. And it works in both directions. So if we had to find the probability of 2 or more hurricanes in a 3-year period, we need to change lambda from 6 to 18. Okay, because up here, we had 6 per year. Now we want to know per 3-year period. And then we'd work out the probability of x greater than or equal to 2, which is 1 minus the probability of x less than or equal to 1. Okay, so that's adjusting for time intervals. Another thing you often have to do is to decide whether real life does fit a Poisson distribution. So there are 2 things to do when you've got to work that out. Suppose you've got a bunch of real life data. Well, the first thing you do is you work out the average value, and then you work out the variance. Because we know if a Poisson distribution fits a situation, those 2 things are exactly the same. So when we do it with real life data, we ask, are those 2 things similar? I'm going to be a little bit loose on what similar is, but again, we'll see that when we start working through some examples. Most of the ones in the book, it's pretty clear because they've designed them to be really close together. Okay, so if they're similar, then we can approximate x with a Poisson distribution, and lambda will just be whatever our average was from our real life data. And then what we do from there is we take our Poisson distribution and we figure out a whole bunch of theoretical probabilities, and we compare them to what actually happened in real life. Okay, so the thing that's been missing from all of this is talking about what exactly does a Poisson distribution look like. And we did this a little bit last term, but it depends hugely on the value of lambda. Okay, so sometimes a Poisson distribution is skewed, and sometimes it's symmetric. So I could make you do a whole lot of that by hand, but luckily GeoGebra will do that for us really easily. So I've done some screenshots, but you might like to jump onto GeoGebra, and the module that you want is called the Probability Calculator. So you can play around with this yourself, and I think that's a really good thing to do. But I've put enough screenshots in that hopefully you'll notice something. So take a look at the next few. I'm just going to scroll through them and then come back. And I want you to think about what we could maybe do in some situations to get away from having to work out Poisson probabilities. So here we go, let's take a look. So this one has got a really low lambda of 0.2, and the graph looks very weird because it's showing negative numbers, but don't worry about this. This is the probability bar for 0, this is the probability bar for 1, and this is the probability bar for 2. So it's extremely heavily skewed. Nearly all of the weight is around 0 and 1. Here, we've moved up to lambda equals 1. In this one, we're moving up to lambda equals 2. So what are you starting to see here? Right, now we're up to lambda is 5. And the skewness is still here a little bit. The other nice thing is we're starting to see a pretty low value down here at 0. Think about why that might be nice. Now we're going to move lambda up from 5. I'm going to jump up to lambda is 15. Okay, so I want you to just jot down, what does this make you think that we could use to approximate a Poisson distribution, and how might you go about doing that? Right, this is the last one. This is an extreme case. This is lambda of 40. Right, so in case you hadn't guessed, what we're getting at here is that we can quite often approximate a Poisson distribution with a normal distribution. And the rule that we're going to use in A-level to do that is that we can do that when lambda is equal to 15 or more. I don't know why I wrote it like that. Let's put it like that. Lambda is greater than or equal to 15. Now, the reason we're going to stick with 15 for that rule is that when we've got a normal distribution, we've got nearly all of the probability within 3 standard deviations. And if we pick lambda being 15, it means that we're not going to have much, if any, of my distribution in nonsensical negative number territory. Okay, so actually 15 is a little on the conservative side, but that's what we're going to stick with because that's the A-level guideline. So if lambda is 15, it's fine to approximate a Poisson with a normal distribution. And we might want to do that because normal probabilities are really easy to find. So how are we going to do it? Well, it's really easy. We know that the expected value of a Poisson is lambda, and the variance of a Poisson is also lambda. For a normal distribution, we need to have mu, and we need to have sigma, the standard deviation. Standard deviation is just the square root of the variance. So this is what I'm going to do to use a normal approximation. What do we have to watch out for? I know what I was thinking about there. The Poisson values are discrete. So they are 0, 1, 2, 3, and so on. The normal values are continuous. So we have to do what's called a continuity correction. Right? So if I said I want you to work out the probability of x equals 3, when I turn to the normal distribution, I want to have a whole bar. Right? We know that with a continuous distribution, that probability is going to be 0. So what we're going to do instead is go back, oops, sorry about that, we're going to go back to x between 2.5 and 3.5. Okay, now that's explained really well in the book, and I'll talk about that more in class, but I'm limited to pretty short videos with this screencasting software, so I'm trying to blast through everything in about 14 minutes. Okay, so we can approximate a Poisson with a normal distribution when lambda is 15 or more, and it's really straightforward to do, but we have to watch out to do this continuity correction thing. The last one is that we can go backwards. And this one I'm just going to touch on here because it comes up in the exercises, and I'll do some more of this in class tomorrow or Tuesday, and that's that we can go the other way around. Sometimes we can use a Poisson to approximate a binomial. Now, the reason we want to do that is that binomial probabilities are really painful to work out because remember I've got the 3 bits, right? I've got NCX, p to the x times 1 minus p to the n minus x. So we can do a Poisson approximation of a binomial in these situations. We have to have 3 conditions. We have to have n big, so n has to be greater than 50. P has to be small. I'm not going to quantify small, but NP, because the size of P depends on this, NP can't be too big. So NP, the mean, has got to be less than 5. So this is kind of the opposite of a normal approximation. Right here we're wanting to use a Poisson, and we're using it to approximate a binomial. Okay, so my time is nearly up. You will be saying, thank heavens for that. That means that you can now go off and do a whole bunch of practice in the textbook. The questions are really good. So all of, I think, 9A through to 9C is now completely doable. The only thing I haven't done in here is how to do hypothesis tests for Poisson variables. If you want to, you're welcome to go and have a look at that. That's the last bit of 9D. Thanks for watching. Let me know if this makes any sense and which examples you'd like me to go over.